Good evening, dear students. So myself, Richa Patil, and I'm your chemistry teacher. Okay, so I'll be taking today. I'm going to teach the topic that is haloalkanes and haloarenes. Okay, so shall we start? Yes. Okay. So haloalkanes and haloarenes. So this is the first chapter in your PUC. That is your second year. Okay, syllabus from the organic chemistry. Okay, so you start with this chapter that is haloalkanes and haloarenes. So what do you mean by haloalkanes, students? Yes, what do you mean by haloalkanes? So we know what are alkanes. Okay. For example, if I give the example of methane, so it is a alkane, right? Now, so this particular methane, it has 4 hydrogen atoms. Okay. So when this one of the hydrogen atom, when it is replaced by a halogen, okay, then we call it as haloalkanes. Okay. So if I give you a general definition of haloalkanes, so they are the alkyl halides. What we call them? They are the alkyl halides. Okay. So these haloalkanes and haloarenes. So these are the derivatives of hydrocarbons. Okay. What do we mean by haloalkanes? First, we'll discuss. So haloalkanes, which are called as alkyl halides. Okay, they are the halogen derivatives. Okay, what are they? They are the halogen derivatives. Okay, of this aliphatic hydrocarbon. I hope you know what is do you mean by aliphatic hydrocarbon. Aliphatic hydrocarbon means they are the straight chain compounds. Okay, when carbon-carbon bond they are linked. Okay, they are called as the aliphatic hydrocarbon. So haloalkenes, they are the halogen derivatives of aliphatic hydrocarbon, where 2 or more hydrogen atoms we can replace by halogen atoms. Okay, here the halogen atom which is attached to the carbon, it is what hybridization? It is sp3 hybridized. Okay, it is sp3 hybridized. So we call them as haloalkanes. Okay, so replacement of hydrogen atom in hydrocarbon, okay, which is sp3 hybridized, it is the haloalkane. So the resulting compounds are called as haloalkanes. Now, what do you mean by haloarenes, students? What do you mean by haloarenes? So these are also the halogen derivatives. Okay, these are also the halogen derivatives. Now here the halogen, so these are the halogen derivatives of what? They are the aromatic hydrocarbon. Now what do you mean by aromatic? Aromatic means when they are in the form of ring structures. Okay, that is your benzene ring. So when they are benzene associated rings, okay, compounds are there. So to that, so when the so they are the halogen derivatives of what? Of aromatic hydrocarbons, okay, in which 1 or more hydrogen atoms, they are replaced by the halogen. Now here, the halogen atom to which it is attached, okay, to which the carbon is attached, it is sp2 hybridized. What do you mean by sp2 hybridized? You can see a double bond, right? You can see in the what in your benzene, there is an alternative double bond. So your halogen atom is attached to the carbon, which is sp2 hybridized. Okay, when you have a double bond, you call it as sp2, and in sp3 the carbon are all having a single bond. Okay, so these are the meaning of the word haloalkanes and haloarenes. So these are both the halogen derivatives. Okay, so how do we write the general formula? So the general formula for haloalkanes is Rx. We represent it by Rx. Okay, and the general formula for haloarenes is ARX. Okay, that is AR represent your aromatic ring. Okay, I hope this is clear. The definitions are clear. So further, we are moving to the classification. Okay, so we can classify this halogen derivatives. Okay, based on first the number of halogen atoms, and secondly based on the nature of the carbon to which the halogen is attached. Okay, so first classification is what? On the basis of the number of halogen atom. So how many halogen atoms are present? Okay, so let us see that. So here you can see, okay, so based on, so if there is one halogen atom attached, okay, then we call it as monohaloalkane. Okay, so one halogen atom. So on the basis of the number of halogen atom present, halogen derivatives are classified as mono, di, tri, and tetra. Mono means one, di means two, tri means three, and tetra means four. Okay, so these are based upon the number of the hydrogen atoms are replaced by the halogen. So how many halogen atoms are attached? Now, in the first example, you can see there is only one X. Okay, you can see only one halogen. So it is called as a monohaloalkane. In the second example, you can see there is one. Okay, so this is an example of what? There is a what attached? This is a arene group, right? There is a what? There is a your aromatic ring is present. So halogen is attached to a aromatic ring. How many halogens are present? Only one. So we call it as monohaloarene. Okay, monohaloarene. So this is a alkane group. So it is monohaloalkane. Here there is an aromatic ring. So we call it as what? Monohaloarene. Okay. Here what you can see, there are two halogen in the third example. Okay, third structure, you can see there are two halogens are at, okay, so two hydrogens are replaced by two halogens. So what we call it as dihaloalkanes. What we call it as dihaloalkanes. Why di? Because two halogens are present. So dihalo, and it is an alkane aliphatic group. So we call it as dihaloalkane. Now here in the fourth, what you can see, that three halogen group are attached. So three hydrogen atoms are replaced by three halogen groups. Okay, and this is an alkane. So we call it as trihaloalkane. So this is a first classification based on the number of halogen atoms which are present. Okay, so based on the number of halogen atoms, how they are, the halogen derivatives are classified as mono, di, tri, tetra. Okay, so first classification. Then based on the nature of the carbon, okay, which is attached. So first, when the halogen is attached to a carbon which is sp3 hybridized, okay, when it is attached to a sp3 hybridized, then it is called as what? It is called as alkyl halides. Okay, so so based on the number, so now here so based on the nature of the carbon to which the halogen atom is attached, if the carbon is sp3 hybridized, so if it is like this R dash CH, so this can be a, so how we are going to say this is a haloalkane. Okay, so this is a primary. So this is a primary alkyl halide. So this is what? Primary alkyl halide. Okay. So R dash CH. So one of the hydrogen atom is replaced by your halogen. So this is a primary alkyl halide. Now, if what is a secondary alkyl halide? So that is, so in secondary alkyl halide, you can see that the nature of the carbon to which, okay, there are two alkyl groups attached. Okay, the halogen attached to the carbon with the two alkyl groups. So we called it as secondary alkyl halide. Okay, we call it as secondary alkyl halide. Okay, so here the halogen is attached to the carbon with the one alkyl group. Here the halogen is attached to the carbon having two alkyl groups. So it is a secondary alkyl halide. And here the carbon is attached to the halogen is attached to the carbon which is having three alkyl groups. So this is a tertiary alkyl halide. Okay, this is a tertiary alkyl halide. I hope this is clear. So if the carbon, so then we are discussing the nature of the carbon. Okay, where the halogen is attached. So if the carbon is sp3 hybridized, it is further classified as primary, secondary, and tertiary alkyl halide. Okay, then so next we are going to see there is something called as allylic halides. Okay, there is something called as allylic halides. So in allylic halides, okay, the halogen atom, okay, so the halogen atom is bonded to the sp3 hybridized carbon, which is next to a carbon carbon double bond. So if I give you an example, so this is an example for the allylic halides. Okay, so the halogen, okay, so the halogen is attached to the sp3 hybridized carbon. So this is a sp3 hybridized carbon which is next to a carbon carbon double bond. Okay, so this is called as the allylic carbon. This is called as what? Allylic carbon. Okay, so what do you mean by allylic carbon? So one more time I'll repeat. So the halogen atom is bonded to sp3 hybridized carbon which is next to a carbon carbon double bond. Okay, which is next to a carbon carbon double bond. So one more example of, so it can be like this. Okay, so so this is allylic halides. Okay, so your what halogen is attached to the carbon sp3 hybridized carbon which is next to a carbon carbon double bond. So these are called as the allylic halides. What they are called as allylic halides. So next we are going to discuss about the benzylic halides. Okay, these are the benzylic halides. Now what do you mean by benzylic halides? So benzylic halides here, the halogen is attached to a sp3 hybridized carbon next to a aromatic ring. So this is the example. Okay, this is the example of aromatic your benzylic halide. So halogen is attached to a sp3 hybridized carbon. Okay, so this is a sp3 hybridized carbon next to a aromatic ring. So these are the nature of the carbon when the carbon is sp3 hybridized. Okay. Next, we are going to see if the carbon is sp2 hybridized. Okay, if it is sp2 hybridized, so it is classified as vinyl halides and the aryl halides. So let us see what are vinyl halides. So vinyl halides, okay, so in vinyl halides, the definition for vinyl halides is the halogen atom, okay, is, so in this compounds, your halogen atoms is, it is attached or you can say it is bonded to the sp2 hybridized carbon atom, okay. So this can be a example. Okay, so here you can see, so this is an example of the vinylic halide. So the halogen atom is attached to a sp2 hybridized carbon, which is next to a carbon-carbon double bond. So you can see the difference between what is vinylic halides and allylic halides, right? In allylic halides, what we had seen, the halogen atom is attached to the sp3 hybridized carbon, which is next to a carbon-carbon double bond. In vinylic halide, what you can see, the halogen atom is attached to the carbon, okay, sp2 hybridized carbon which is next to a carbon carbon sp2 hybridized carbon, okay, of a double bond. So that is the definition for vinylic halide. So one more example I'll give you for vinylic halide. So this can be the example for vinylic halides. Okay, so halogen atom is attached to the sp2 hybridized carbon of the carbon carbon double bond. So next we are going to see is the aryl halides. Okay, next classification is aryl halides. So in aryl halides, the halogen atom, okay, is bonded to the, so here you can see, I'll give you example. Okay, so this is example. So in aryl halides, okay, the halogen atom is bonded to the sp2 hybridized carbon of a aromatic ring. Okay, so this is example of your aryl halide. So this is example of your aryl halide. Okay, one more example I'll give. So what it is, the halogen atom is attached to the sp2 hybridized of the aromatic ring, Okay, I hope this is clear. So only for your syllabus, okay, for your board syllabus, you have the nature of carbon of sp2 and sp3. So these things you need to know. Okay, so the nature of carbon, that is primary, primary alkyl halide, secondary alkyl halides. Okay, so that tertiary alkyl halides, what are the allylic halides, what are benzylic halides. When carbon is sp2 hybridized, that is vinyl halides and aryl halides. So these things you need to know. Okay. So let us move further. So this was the, so if the carbon of the CX bond is sp3 hybridized, so you can do the quick revision here. Okay. So when the carbon that is, so what we have discussed, so here the carbon is attached to the one your alkyl group. So here the halogen attached to the carbon having two alkyl groups, so it is secondary. So here the halogen attached to three alkyl groups, so it is the tertiary. Okay. So yes, so these things we have discussed now. Okay, just go through the slides. Okay, so what is allylic benzene? What is a benzylic benzene? So this also we have discussed. Okay, allylic benzene. So halogen attached to the sp3 hybridized carbon, which is next to a carbon-carbon double bond. Benzylic halogen attached to the sp3 hybridized carbon, which is attached to a aromatic ring, is called as the benzylic halides. Then we have discussed if the carbon, that is, if it is sp2 hybridized, right? So this we have discussed about vinylic and aryl halide. So what do you mean by vinylic? The halogen is attached to the sp2 hybridized carbon, okay, which next to a double bond. And here carbon-carbon double bond. Then here aryl halides, halogen attached to the sp2 hybridized carbon of the aromatic ring. Then they are called as what? Aryl. Okay. Okay. So next we are going to, so okay. So here, when we are discussing about the nomenclature, okay, how to name the compound. So here, in the when we are giving the name for the compounds in the haloalkanes, okay. So alkyl halides, we are giving the first the alkyl group, name of the alkyl group, okay, followed by the halide, okay, name of the halide. So that is like haloalkane. So this is the common name, okay, how we are giving. So they are in IUPAC nomenclature, how we are going to name them. We are going to name them as halo substituted hydrocarbon. So, and when we are deriving in case of alkyl halides, okay, aryl halides, we are going to name it as the common name as in haloarenes, okay. So we will see as we are discussing the. So let us see how to prepare the haloalkane. So these are some of the general methods of preparation of haloalkanes. Okay. So we can prepare the haloalkane. So how we can prepare this haloalkane? So there are four. So from alcohols we can prepare. Then by free radical halogenation of alkane, addition of hydrogen halide on alkene. So let us start. So first is with the alcohols. So generally, when we see alcohols, okay, reactions of alcohols, when we want to obtain the haloalkanes, so how we are going to, so how we are going to get, so the general preparation, so we are going to take the alcohol, okay, as the starting reactant, okay, so this is our main reactant. So we are going to react it with the Lucas reagent. So first important reaction, so this is very, very important. Please mark it as important. So alcohol, when we are reacting with Lucas reagent, so there can be a question, what is Lucas reagent? So Lucas reagent is concentrated HCl plus anhydrous ZnCl2. Okay, what is Lucas reagent? It is concentrated HCl plus anhydrous ZnCl2. What we are going to get? So ROH, when it reacts with concentrated HCl plus anhydrous AlCl3, that is ZnCl2, anhydrous ZnCl2. So please remember what is Lucas reagent. So we are going to get RCl plus water. Okay. And this particular reaction is called as the Grooves process. What it is named? It is named as Groove's process. So there can be a question, okay, what is Groove's process? Explain or write the equation, okay, write the general equation, or they can give you what is, so that can be a 2 mark question. And also there can be a question, what is Lucas reagent? What is Lucas reagent, students? Concentrated HCl plus anhydrous ZnCl2, okay, ZnCl2. Next reaction is we can obtain the your haloalkanes from reacting it with the phosphorus trichlorides or phosphorus pentachloride. Okay, so when we react it with so alcohols, okay, when we react it with your phosphorus trichloride, so your X can be your Cl, okay, your X can be your Cl, or it can be Br. So when we are taking, so what we are going to do, we are reacting your alcohols with phosphorus trichloride. I am going to get haloalkanes plus H3PO3. Okay, and H3PO3. So this is the second preparation, that is from phosphorus trihalides. Okay, then we can also get the haloalkanes from phosphorus pentachloride. Okay, so phosphorus pentachloride. So alcohols, when they react it with phosphorus pentachlorides, okay, your X is your chlorine. So what I'm going to get, students? I'm going to get RCl plus POCl3 plus HCl. Okay, so this is another method of preparation of alcohol. Okay, so so these are the, so first, this is the second, okay, with phosphorus trichlorides and trifluoride, trihalides and that is pentahalides. Okay, and the third one is very, very important. So please mark, this is also important. Okay, first one and the third one important. So the third one, that is alcohols when they react it with pyridine in the presence of thionyl chloride. So again a 2 mark question. Okay, write the preparation of alcohols from thionyl chloride. So this can be a question. That is so write the preparation of alcohols. Okay, that is preparation of haloalkanes from thionyl chloride, using thionyl chloride. So how is the reaction? So alcohols react it with what? Please react it with thionyl chloride in the presence of pyridine. Okay, in the presence of pyridine, what I'm going to get? I'm going to get RCl plus SO2 plus HCl. Okay, and this process is called as the Darzens process. Okay, very important, Darzens process. Okay, so what is the reaction? So alcohols, they reacted with thionyl chloride. Okay, they reacted with thionyl chloride in the presence of what? In the presence of pyridine. Okay, we are going to get that is here we are going to get what? That is your this. Okay, so haloalkane. So if I give an example with respect to R, okay, alkyl, if I take it as ethyl. So if I take C2H5OH plus thionyl chloride, okay, in the presence of pyridine, what I'm going to get, student? Okay, so your R is what? C2H5Cl plus SO2 plus HCl. Okay, I'm going to get ethyl chloride. What I'm going to get? Ethyl chloride. Okay, is it clear? So very important. What is Darzens process? So alcohols, when reacted with thionyl chloride in the presence of pyridine, we are going to get substituted haloalkanes. Okay. Now here you can give so practice the example, also the general reaction. Now here this is the what you can say, this method mostly this method is used, okay, for the preparation of your haloalkanes. Okay, why can you say why? So here you can see the byproducts which we are getting, okay, are both the gases. Okay, yeah, so most probably this is the most used preparation for the when you want to prepare the haloalkanes. Why? Because the byproducts are gases. So the gases, we know that when gases are released, they escape out easily. Okay, they escape out easily. So you can the product can be easily removed. Okay, the product can be easily removed. So we are using this process. Okay, now from the preparation, which are the important preparations you have to study, that is the Groove process and the Darzens process. And what is the Lucas reagent? So these three things you have to know. Okay, and why this is the most preferred process? Because the byproducts obtained here are both gases, and gases easily escaped out, and the product can be easily removed. Okay, so this is the uh, answer. Okay, I hope this is clear. Okay, moving on to the next. So we are using in Groove process, we are using what? ZnCl2. Why? To break the, to weaken the COH bond. Okay. So please know this important note. So why we are using ZnCl2, that is your Lucas reagent in Groove process, to weaken your COH bond, that is your alcohol bond. Okay, to broke this. Okay. So because so in case of tertiary alcohol, ZnCl2 is not required. Then the reactivity of halogen acid is Hi is greater than HBr, which is greater than HCl. Okay, so this is the reactivity of halogen acids. Okay, then we have discussed this also, why Darzens procedure is the best method for preparing the alkyl halides, because the byproducts obtained are both gases. Okay, and they can escape out easily. Okay, fine. Then the next method is free radical halogenation of alkanes. Okay, from free radical halogenation also we can obtain our substituted haloalkanes. So what we are doing here, we are taking what? So this is a butane. Okay, butane is reacted with chlorine in the presence of your UV light. Okay, so free radical halogenation means what? It always takes in the presence of a halogen and light. Okay, so this is required. So free radicals are generated. So what will happen? So your hydrogen, okay, one of the hydrogen will be replaced by your halogen. Okay, so it can either attack this carbon or it can attack this. So these are the two products. So I'm going to get a butane. Okay, that is a chlorobutane, and I have to get a what? Secondary butane here. Okay. So you can see this is a primary. So this is a substituted haloalkanes. Okay, so two products I have got here. Now here what you can say, so butane, so free radical halogenation of alkanes always takes place in the presence of a halogen. So here the halogen is your chlorine and we are supplying UV light. Okay, so what will happen? One of the hydrogen here, okay, the it can be replaced here by the Cl. Here again one in the other product, what will happen? The second hydrogen atom is replaced by the chlorine. Okay, so like this. Then very important. Now when we have a alkane, okay, when you have a alkene, now if I want to add a halogen halide, okay, that is I'm going to add a hydrogen halide. Now here when I am adding, so this is what? Across the double bond, the number of carbon atoms are same, right? The number of carbon atoms are same across the double bond. So what will happen? How the addition will takes place? Yes, how the addition will takes place? At one carbon, at any one carbon, your hydrogen will be added. At any other carbon, your bromide will be added. So this is the addition product. Okay, this is the addition of the hydrogen halide taking place. So these are type of alkenes. Okay, when you have the same number of carbon atoms on either side are called as what? Symmetrical alkenes. Okay, they are called as the symmetrical alkenes. Okay, when you have same number of carbon atoms on either side, they are called as what? Symmetrical alkenes. Okay, so whenever symmetrical alkene are present, okay, on either side of the carbon, anywhere it will be added. Okay, now when you have like this, okay, when you have such type of carbon, okay, now what will be happening? What will happen here? How you can add this hydrogen halide? Yes, how will add this hydrogen bromide here? Yes, so like that time we have to follow one rule. That rule is called as the Markovnikov's rule. Okay, what it is called as Markovnikov's rule. Now, what is this Markovnikov rule, student? So, in Markovnikov rule, so whenever you have the unsymmetrical alkene, okay, whenever we have the unsymmetrical alkene, so the molecule of the hydrogen halide, okay, it will be added, okay, it will added in such a way that the that the halide will be added to the carbon having least number of hydrogens, and hydrogen will be added to the carbon with more number of hydrogens. Okay, so like this, that is so one more time I'll repeat. So Markovnikov rule, what do you mean by Markovnikov rule? So here, whenever you have an unsymmetrical alkene, so we know that whenever symmetrical alkenes are there, the addition can take place in any carbon. Okay, any carbon, it will add one hydrogen will be added in on another carbon, bromide will be added. Now, whenever we have unsymmetrical alkene, unsymmetrical means what? The number of carbons, okay, on either side of the double bond is not same. Now, here only one is there, here two are there, okay. So, that time how this hydrogen halide will be added. So, this is the positive part, this is a negative part. So, the negative part will be added to the carbon, okay, with the least number of carbon with the least number of hydrogen atoms, and the positive part, okay, and the positive part will be added to the carbon with more number of hydrogen atoms. So what will be the product? So CH3, CHI and CH3. So this is the product. So this is a major product. Okay, whenever you have the unsymmetrical alkene. I hope this is clear. Okay, so now, so this is your Markovnikov rule. Now there is something called as anti-Markovnikov rule. Now what do you mean by anti-Markovnikov rule, student? So anti-Markovnikov rule means, okay, it will be opposite. Okay, it will be opposite to Markovnikov rule. So CH3, CH double bond, CH2 plus HBr. So anti-Markovnikov rule, it takes place in the presence of your peroxides. Okay, any peroxide. So any peroxide is there. Okay, then what will happen? It is understood that it is an anti-Markovnikov rule. Okay, whenever on the arrow mark peroxide is written, okay, then it is understood what? It is understood that it is a anti-Markovnikov. It will be reverse. So what will happen in anti-Markovnikov rule, students? So the hydrogen, first we'll see the negative part of the hydrogen halide will be added to the carbon with more number of hydrogen atoms, and the positive part will be added to the carbon with least number of hydrogen atoms. So what will be the answer? So CH3, CH2, CH2, Br. So this is the major product. Okay, this is the major product. So what is anti-Markovnikov? How you will understand that it is anti-Markovnikov or Markovnikov? So on the arrow mark, if it is written peroxide, that means it is anti-Markovnikov. And on the arrow mark, if it is not written anti-Markovnikov, means it is Markovnikov. Okay, so here you can see this is anti-Markovnikov and this is Markovnikov rule. Okay, I hope it is clear. So I'll repeat what is Markovnikov rule. So in Markovnikov rule, the negative part of the hydrogen will be added. The negative part of the hydrogen halide will be added to the carbon with least number of hydrogens, and the positive part of the hydrogen halide will be added to the carbon with more number of hydrogens. Okay, yes, fine. Let us go further. So yes, so you can see the addition of halogen. So this is the addition of halogen. So when I have a triple bond and when I want to add halogen, so what will happen? First, one of the bond will broke, and what will happen across the double bond? Your one halogens will be added. Now again, if I want to add the halogen, again the second bond will be broken, and I'm going to get what? All single substituted product. Okay, so I can take any halogen. My halogen can be Cl2 or it can be Br2. Okay, I hope it is clear. So from the triple bond, so here is the example. So I'll take one example, CH3C triple bond CH in the presence of Br2. Okay, what I'm going to get? So where the addition takes place across the triple bond. So first what will happen? CH3C, okay, Br, then double bond CH, Br. Okay, now again further I am going to react. So first only one bond is broken and double bond is added. Okay, that is at across one bond, your Br is added. Okay, one bond is broken and Br atoms are added. Now again I want to do the addition. So what will happen now? Here I'm going to get Br, okay, Br and Br. So all the, so stepwise. So when one molecule is added, only one bond is broken. Again, when we add another molecule of your bromine, then another bond is also broken. So this is the addition. So see how much molecules are going to add. Okay, if it is one, only one bond will be added. If another one more, if it is told to add, then uh, uh, the next bond is also broken. So triple bond means one bond will be broken. If they give you like this, CH3 double bond, CH2, CH3, okay, CH2, CH3 like this. So what will happen? Plus Br2. Now what will happen? It will be CH. Okay, so it will be CH here. So what will happen now? So here one Br will be added, and the here one Br will be added, and it will be CH3. Okay, so like this. Got it? Yes. So this is the addition of halogen. So we are seeing the addition of halogen. So next method is for the halogen exchange method. Okay, next is the halogen exchange method. So very important name reactions, that is Finkelstein name reaction. Okay, very important, that is Finkelstein's reaction and Schwarz reaction. So very important, please mark it as important, students. Mark it as very important, students. Okay. So what is Finkelstein's reaction, student? So Finkelstein's reaction. So I'll read. Okay, I'll read. So they are called as the halogen exchange method. What we call them? We call them as halogen exchange method. So alkyl chlorides, okay, or bromides. So you can see here in the general reaction what is mentioned, students. Can you see the general reaction? Rx. Can you see here? Yes. Rx. Okay. Rx plus NaI. Okay. I'll write it here. Rx plus NaI in the presence of acetone. Okay. So your X can be chloride or bromide. I'm going to get Ri plus NaX. Okay. So I'll read. Okay. I'll tell you the definition for Finkelstein's reaction. So alkyl chlorides or bromides, okay, when they are reacted with sodium iodide, when they are reacted with what? Sodium iodide in the presence of what? In the presence of acetone, okay, we are using acetone, we are going to get iodoalkanes, okay, or we are going to get the alkyl iodides. Okay, we are going to get alkyl iodides, or we say it as iodoalkanes plus NaX plus NaX. So this is the Finkelstein reaction. So I can take R as CH3 and X as Cl. So what is the name here? What is the name, students? It is what? It is methyl chloride. Okay, it is methyl chloride. So I'm going to react this methyl chloride with sodium iodide in the presence of acetone. What I'm going to get, students? I'm going to get methyl iodide. I'm going to get what? Methyl iodide. Okay. Plus sodium NaCl. I'm going to get sodium chloride. Okay. Example. So it can be a question. Explain Finkelstein reaction with an example. 2 marks question. Very important. 2 marks question. Explain Finkelstein reaction with an example. Okay, so this is a general reaction. This is a general reaction and this is a example. So you need to know the general reaction also. You need to know the example also. Yes, and you have to explain it also. So how we'll explain? So alkyl chlorides or bromides, when they react with the sodium iodide in dry acetone, What it forms? It forms alkyl iodide. Okay. So this reaction is known as Finkelstein's reaction. Okay. This reaction is called as what? Finkelstein reaction. I hope it is clear. Yes. Okay. So mark this as important. Okay. So the next is also important. That is your Schwarz reaction. That is your Schwarz reaction. So again, this is also a halogen exchange method. What we are doing, we are just replacing the halogens. Here we have taken Cl or it can be Br. It is replaced by the iodide. Okay, fine. Next is the Schwarz reaction. So let us see what is Schwarz reaction. So Schwarz reaction is also when alkyl chloride or bromide, okay, they are heated with your metallic fluorides. Okay, they are heated with what? Metallic fluorides. Okay, we are going to get what we are going to get. We are going to get the this what metallic fluorides. We are going to get the alkyl fluorides. What we are going to get? Alkyl fluorides. Okay, plus your metallic fluoride is obtained. So this is, so when I want to exchange, when I want to get the iodoalkanes, we are going to use Finkelstein reaction. When I want to get alkyl fluoride, I am going to get Schwarz reaction. So either, so alkyl fluorides of bromide, we are going to react it with metallic fluoride. So which are the different metallic fluorides? I can take AgF, I can take Hg2F2, okay. Then I can take cobalt, that is COF2, okay, or I can take SbF3. So these are the metallic fluorides. So these are some of the examples of metallic fluoride. So either of this you can take and you can react, okay. I'm going to get what? Alkyl fluoride. So let me give you example. So let me take R as C2H5, okay, C2H5 and Br. So what is that? Ethyl bromide. Okay, it is a ethyl bromide. I'm going to react it with AgF. What is AgF? Yes, what is AgF, students? So silver fluoride, right? I'm going to get a, so I'm going to react it with the silver fluoride. Okay, and what I'm going to get? I'm going to get ethyl iodide. Okay, I'm going to get a ethyl iodide and I'm going to get AgBr, that is silver bromide, okay, as the byproduct. So this is an example. So please study with the general reaction and example. Okay, please study with general reaction and example. So these are both the halogen exchange method. Okay. So these are both the halogen exchange method. So first is the Finkelstein reaction. The second is the Schwarz reaction. Okay. I hope this is clear. Okay. So both are very important. Both are very important. Okay. So you can use these metallic fluorides. Okay. You can use these metallic fluorides for the preparation of alkyl fluorides. Okay, so please study. The question can be explain Finkelstein reaction with an example, or they can ask you give the general equation of Finkelstein reaction. So you need to know your the definition, the general reaction, and one example. Okay, for both Finkelstein and Schwarz. Okay, let us move further. So next we are going to see the general methods of preparation of aryl halides. Okay, next we are going to see the general methods of preparation of aryl halides. Okay. So first one is by halogenation. Okay, by halogenation of aromatic hydrocarbons. Okay, by halogenation of aromatic hydrocarbons. So aryl halides means what? The halogens are attached to the aromatic ring. Okay, aromatic substituted. Okay, so first is by halogenation of aromatic hydrocarbon. Second is by side chain halogenation. Third one by benzene disonium salt, and the fourth one is from phenol. Okay, from phenol. So these are the general methods of preparation of aryl halides. So first one is that is by halogenation of aromatic hydrocarbons. Okay, so we have taken a benzene. We have taken what? We have taken benzene. We are reacting with chlorine. Okay, in the presence of FeCl3, and the condition is dark. We are maintaining a dark condition. Okay, at a temperature of what? 310 to 320 Kelvin. Okay, so what we are doing, we are taking an aromatic ring, okay? We are reacting it with chlorine, okay? In the presence of FeCl3, a dark condition, 310 to 320 Kelvin, we are going to get what? Chlorobenzene. We are going to get chlorobenzene plus hydrochloric acid as a byproduct. Is it clear? Okay, so this is the your what first preparation, okay, of aryl halide. So by halogenation of aromatic hydrocarbon. So please, okay, understand this. So we can do the preparation of this your aryl chlorides, or you can prepare any. These are the aryl chlorides, right? So you can prepare any aryl chlorides, or you can prepare any aryl bromide. So if I want to prepare bromide, what I'll do here Br2. Okay. So I can take here FeBr3. Okay. So other things will be same. So what are the other catalysts we can use? I can use FeCl3. I can use FeBr3. I can use AlCl3. Okay. So these are the different catalysts we can use. So we can do, so what type of reaction it is? It is a electrophilic substitution. Okay. It is undergoing what? Electrophilic substitution. So we can prepare alkyl chlorides or bromides, okay, by electrophilic substitution, okay, of what? Arene. So we can use the chlorines and bromine respectively, okay, and these are the catalysts which we can use. Yes. So next is the side chain halogenation. By side chain halogenation, so what we are doing here, we have taken a toluene. Okay, this is a toluene. Okay, what we are going to do, we are going to react it with chlorine. We are going to react it with what? Chlorine. Okay, at a what? 383 Kelvin. So the temperature is 383 Kelvin in the presence of sunlight. Okay, we are using sunlight. What will happen? One of the hydrogen, okay, one of the hydrogen here, it is replaced by what? It will be replaced by Cl. Again, so again the step is reacted, okay, again we are doing side chain halogenation. Again we are supplying some chlorine, okay, and again we are supplying some what? Sunlight. So again what will happen? Again there are halogens here, hydrogens here, okay. So again one of the hydrogen will be replaced by what? Cl2. So your CH3, so what will happen? It will become CH2. Again, when you do chlorination and halogenation, okay. So again, they have done chlorination and your halogenation with respect to light, okay, in the presence of light. What I'm going to get? CH, okay. So CH3 will be replaced by CH2Cl, then again CHCl2. Again, so there are again replaceable hydrogen atoms. So again, side chain halogenation can be done. And what will happen? All the halogens are replaced by what? Again, all the halogens are replaced by your halogen atom. All the hydrogens are replaced by your halogen atom. So this is the side chain halogenation. So how this side chain halogenation occurs? At a very high temperature, that is 383 Kelvin, in the presence of light and your halogen. Okay. So if I want a chlorine as a side chain, the halogen, so I have to take chlorine only. If I want bromine, so bromine in the presence of light. Okay. So what I have got? I have got the last product. Okay, what I have got is a benzo trichloride. Okay, it is a benzo trichloride. So all the hydrogens are replaced by what? All the hydrogens are replaced by your halogens. Okay, so this is a side chain halogenation. Next, from benzene diazonium salt. So firstly, we'll understand how we are going to get this benzene diazonium salt. Okay, how we are going to get the benzene diazonium salt. So benzene, okay, we have to react this benzene in the presence of nitrating your this what? Nitrous acid. Okay, so HNO2. So how we get this HNO2? That is concentrated HCl in the presence of NaNO2, sodium nitrate, I'm going to get this nitrous acid. Okay, I'm going to get this nitrous acid. So how I'm going to get? So benzene, your aniline, sorry, your aniline. So the starting product is aniline. Okay, aniline, we are going to react it with nitrous acid. Okay, how we obtain this nitrous acid? By reacting concentrated HCl and NaNO2. I'm going to get HNO2. Okay, and what I am going to get? I am going to get the disonium salt. Okay, N2Cl. So this is N2Cl. So this is benzene disonium salt, BDS. It is called as BDS, benzene disonium salt. Okay. So please remember how we are going to get benzene disonium salt. That is by the starting reactant is aniline and concentrated HCl and NaNO2. From that we are going to get nitrous acid. What it is called? Nitrous acid. What is nitrous acid? Nitrous acid is HNO2. How we obtained it? By reacting concentrated HCl and your NaNO2, sodium nitrate. Okay. So we are going to get the nitrous acid. Fine. So let us see now how we can do the reaction on this BDS, that is benzene disonium chloride. How we are going to react, okay? How we are going to get the okay, how we are going to get the different name reactions here. So benzene disonium chloride, I hope you understood how we get this benzene disonium chloride. So if anybody asks you how you obtain this benzene disonium salt, you have to tell when aniline reacts with concentrated HCl and NaNO2. Okay, what you get? You get from this what is generated? HNO2. Okay, nitrous acid is generated. We are going to get benzene disonium salt. This we are going to get. Okay, so now on this benzene disonium salt, further if we react it with, okay, further with when we react it with cuprous chloride. Okay, cuprous chloride is what? CuCl. Cuprous chloride is CuCl. In the presence of hydrochloric acid, in the presence of hydrochloric acid, I am going to get a chloro substituted benzene. Okay, I'm going to get a chloro substituted benzene. That is chlorobenzene plus N2 gas will be liberated. Okay, similarly, if I use cuprous bromide, okay, if I react it with cuprous bromide in the presence of what? That is hydrogen bromide. Okay, if I react it with cuprous bromide in the presence of hydrogen bromide, I am going to get a bromo substituted. Okay, I'm going to get what? Your bromobenzene. I'm going to get a bromobenzene plus your N2 gas will be liberated. Plus your N2 gas will be liberated. Now these two are called as the Sandmeyer's reaction. What they are called as, student? They are called as the Sandmeyer's reaction. Very, very important. Okay. Again, very important name reaction. Please mark this as important. Please mark it as important. So benzene disonium chloride, okay, salt, okay, benzene disonium salt. When you react it with cuprous chloride or cuprous bromide in the presence of hydrogen chloride, okay, or hydrogen bromide, we are going to get the halo substituted benzene. Okay, if we react it with chlorine, cuprous chloride, we are going to get chlorobenzene. If I going to react with it cuprous bromide, okay, I'm going to get a bromobenzene with N2 gas. Okay, with N2 gas will be liberated. So this is the Sandmeyer's reaction. Very important again. So they may ask you, explain Sandmeyer's reaction with an example. 2 marks question. Okay, 2 marks question. Fine. Again, let us go for the next. So again, benzene disonium chloride. Okay, your benzene disonium chloride. React it with copper. Okay, reacted with copper in the presence of HCl. In the presence of HCl, what I am going to get? What I'm going to get? I'm going to get a chloro substituted benzene. Okay, plus N2 gas is liberated. Again, copper in the presence of HBr. Okay, I'm going to get a bromobenzene plus N2 gas is liberated. That is called as Gattermann reaction. That is called as what? Gattermann reaction. What is the name reaction, student? It is a Gattermann reaction. Okay. Is it clear? Yes. So copper. So copper, cuprous chloride or cuprous bromide with the presence of HBr and HCl. Okay. It is the Sandmeyer reaction. Copper in the presence of HCl, copper in the presence of HBr. Okay. Chlorobenzene or bromobenzene plus N2 gas will be liberated. It is the Gattermann reaction. Again, very important. Okay, very important. So your BDC, your benzene diazonium salt, when it is reacted with this, okay, you are going to get Gattermann reaction. Is it clear? Okay. Then, so first one is important here. Okay. So here the first one is important, then second one is important, then come to the last one. Okay, last. So this is not there for your syllabus. Okay, this is not there for your syllabus. Let us go for the last one. So again, benzene diazonium chloride. Okay, benzene diazonium chloride N2Cl. When it is reacted with Ki. Okay, I'm going to heat the Ki. What is Ki, students? It is potassium iodide. It is potassium iodide. So when I react your benzene diazonium chloride with potassium iodide, okay, what I'm going to get? Yes, anybody? Can you answer? What I'm going to get? Yes, please answer. What will be the answer, students? So by seeing the above, okay, what you feel, what will be the answer here? We are going to get a halo substituted benzene. Yes, I have given you the clue also. Now, which is the halogen? Or which will be the halogen here? Yes, which will be the halogen? Anybody? Yes, let me see how much you have understood. Yes, which will be the halogen here? Which halogen is present? It is the iodo. Right, I'm going to get the iodobenzene. I'm going to get what? Iodobenzene plus N2 gas will be liberated. Okay, so another your this okay reaction. So again, so from this, so replacement of your diazo group with the iodo group. Okay, we can do it by heating with Ki. By heating with Ki. Okay, fine. Let us go further. So these are some of the preparations of aryl halide. So next is the physical properties. Next, we are discussing the physical properties of haloalkanes. So boiling point, okay. So boiling points of the this, okay, your halogen. So it depends on what? So as the molecule is smaller in size, so what will happen to the molecules? Yes. So as we know now, the halogens are attached. Okay, so halogens will be attached to the your hydrocarbon. So the molecules of these organic compounds. Okay, as we know, they are generally polar. Okay, what do you mean by polar? Polar means your halogens are highly electronegative. Okay, so what they will do? They will tend to pull the electron towards itself. So as a result, the bromide will is partial negative and your alkyl group will be partial positive. So these are called as the polarity. Okay, so polarity will be developed on this particular molecule. So as a result, as the molecule as having high polarity, so there will be high molecular mass. Okay, as compared to your hydrocarbon, your substituted halogens. Okay, your halogen derivatives are having higher mass. Okay, so what will happen? So there is a strong intermolecular forces present. Okay, so intermolecular forces are also stronger in this halogen derivatives. So as compared to your hydrocarbons, your halogen substituted compounds are having high melting point at boiling point. Okay, as compared to your hydrocarbons, okay, of the same molecular mass. Okay, but when you see your halogen substituted as compared to your hydrogen, your halogen atoms are having higher mass. Okay, and as a polarity is also there, so your melting point and boiling point of this halogen substituted compounds will be more. Okay, yes, fine. So this is about the halo boiling point. Then when we see the strength, so when we see the strength also, okay, so when we see the strength also here, so it will decrease. Okay, it will decrease. The strength of the haloalkanes will also decrease as the size of the halogen atom increases. Okay, now when we see the smallest is the fluorine, then is chlorine, then is bromine, and is the iodine. So iodine has the larger size. So as the so the strength of the haloalkanes, what will happen? It will decrease as the size of the halogen atom increases. So the order of the strength is CH3F, okay, it is the strongest, and your CH3I will be the the bond strength is less here. Okay, as the size of the halogen atom increases, the bond strength will decrease. So remember this. Okay, fine. Then we are going to see about the dipole moment. Okay, what is the dipole moment? Yes, so dipole moment, it is also based on the polarity. Okay, so dipole moment decreases as the electronegativity of the halogen decreases. So more the polar atom attached to the your alkyl group, okay, more will be the dipole moment. Okay, more will be the dipole moment. So as the electronegativity of the halogen decreases, okay, so what will happen to the dipole moment? It will also automatically decrease. Then when we see the haloalkanes, okay, these haloalkanes, they are as they are polar. Okay, we have understood now what is polarity. So polarity is developed when you have a higher, that is the more than the alkyl group, your halogen atom. Okay, as it is highly electronegative, so it will tend to pull the electron towards itself. So we say it as polar. So haloalkanes, as they are polar, but they are insoluble in water. Okay, they are insoluble in water as they do not form any hydrogen bonding with water. So they do not form hydrogen bonding. Okay, they are polar, but still they are insoluble in water. Why they are insoluble in water? What is the reason? Because they cannot form the hydrogen bonding. They cannot form. Okay, they cannot form the hydrogen bonding. So because of this reason, the haloalkenes are what? They are polar. They are insoluble in water. Then density. Okay, what about the density? So here density is in the order of IR is greater than IBR. So density is what? Mass upon volume. So more the mass, more will be the density. Okay, so iodide will be the greatest. Okay, Ri is greatest, then RBR, then RCl and RF. Okay, so this is the density order. I hope this is clear. Yes. Okay, so these were the things which we have discussed today. So in the next class, so today, in today's class, what all things we have discussed. So just we will recap. Okay, so we have discussed about what are haloalkanes, what are haloarenes. Then we have discussed about what is the classifications. Okay, we have discussed the classifications of haloalkanes and haloarene based on this, okay, hybridization of carbon and the nature of the carbon, okay, nature of the carbon to which it is attached. Okay, then also we have discussed about what? Then we had started with the methods of preparation. Okay, we have discussed about the methods of preparation also of the haloalkanes, and also we have discussed the methods of preparation of haloarenes. Okay, then we have discussed the physical properties. Then we have discussed the physical properties also. We have discussed the physical properties also, okay, of the haloalkene. So in the next class, we are going to discuss about the chemical reactions of haloalkenes and the remaining things. I hope you have understood in today's class, okay. So the same we are going to continue in the tomorrow's class, okay, fine. So yes, so I shall end this session here. So we'll meet in the next class. Thank you.